So this is UKMT Junior Math Challenge 2020. You get 5 points for every question in the first 15, 6 points thereafter. You don't lose any points for getting anything wrong, so you may as well guess every question you can. Otherwise, let's get straight into it. So which of the following is not prime? Okay, you could just try multiplying some prime numbers together to try and find one of these things. Or you can remember the only prime divisibility rule that I know, which is if the sum of the digits of a number is divisible by 3, that number is divisible by 3. So the sum of these digits is 3. So this is a multiple of 3 here, or it's divisible by 3, doesn't matter how you say it. It's actually 3 times 37, I think. So this one is not prime. And that's kind of what I did when I checked each one, and I eventually got to there. Question 2, there are of course other things you could do, just testing stuff. So to divide by 20, I'm going to divide by 10 and then divide by 2, or divide by 2 then divide by 10. It really doesn't matter. In either case, it ends up being quite straightforward, and you get your answer. Question number 3. So I was kind of surprised to see this question here. You need to know what rotational symmetry of order 2 means, which I don't think I would have known in year 7 or 8, but whatever. That just means if you spin it 360 degrees, it looks the same twice. So it's allowed to look the same after 360 degrees, which clearly this one will, but it also needs to look the same somewhere else. Now we can see this one, if it turns 180 degrees, it's going to look the same, and then it's also going to look the same after 360 degrees, so that one is fine. That one works. This one doesn't, because when you rotate it 180, the two lines are going to be down here, so that one doesn't work. This one, likewise, the line is going to be up there, so it's not going to look exactly the same. This one is going to look exactly the same because this line rotates around 180 and this corner here will be up there, thus making this line look the same. So this one will work, and so will this one obviously, because when you turn it around, this line stays in the same place. So 3 of them stay the same twice and therefore have rotational symmetry order 2. 4. So 1 meter is 100 centimeters. Hopefully we all know that. So if I times this by 66, I get 66 meters is 6600, as the Americans would say, centimeters. Now I didn't bother to do exactly this, but I can see very easily that this is going to be this one here, because it's by far the closest. So yeah, cool. Question number 5. So you think of a number, double it, add 9, divide it by 3, and take away 1, and the number is the same as it was originally. So what number could this be? Well, you could do some algebra here, or you could just test them, right? 1 doubles to 2, add 9 for 11, divide by 3. Well, that doesn't work very well. So let's just stop this here. Let's try the next one. So 2 doubles to 4, add 9, divide by 3. Again, that doesn't go very well, so we're going to say it's not that. C, 3 doubles to 6, add 9 is 15. That does divide by 3 quite nicely. But then when you take away 1, you don't end up with the thing you started with. So that doesn't work. Next one doesn't work either. 17 won't divide by 3 very easily, so stop there. And the answer turns out to be E. Now, I'm convinced, having done quite a lot of Math Challenge, that as soon as they write a question that they think you might just do trial and error for with the answers, they put the answer over at the end. So maybe you should just, if you're going to do some trial and error, start at the right and work left, because in this case the answer was E, and they just trolled you and wasted all your time testing these when the answer was the last one. So have a think about that if you want to. You could also, of course, do some algebra to solve this problem, as I said. Do that if you want to as well. When you've got adding and subtracting like this, just go left to right. So I know BidMath tells you to do addition first, just go left to right though, is technically more correct. So just do these two first to make a 12th, and then do, so that's just combining the first two, everything else stays the same, then combine those two to make 5 twelfths, then these two to make 2 twelfths, then these two to make 4 twelfths, then finally 3 twelfths, which simplifies to a quarter. And we get our answer. 7, 4 positive integers multiply to 110. Now 110 is clearly 2 times 55. I was going to say 11 times 10, which also works, but it's also 2 times 55, and then 55 is 5 times 11. So here are 3 positive integers multiplying to make 110. How do I get 4 positive integers to do it? Well, I just also times by 1, right? Because why not? So these are the 4 positive integers, add them up, and we get our answer of 7 plus 11 is 18, plus 1 is 19. So a grid of 6 cells wants to color 2 of the cells black like this and this, such that 2 black cells share a vertex. A vertex is a fancy word for a corner, but not a side. So he can't change this and this in, because then they would share this side, but this is fine because they just share a corner and not a side. And how many ways can you do this? Well, here's one way. Here's another way. That seems like the next most obvious. But you can also use these 2 corners in here, right? Because then they'll just share one corner here. But then I could use this and this up here, or this and this over there, and I think that will be all of them. And I just kind of vaguely, very quickly sketched these in and drew them. I looked at it for another 30 seconds just to make sure I couldn't see another one, and then I was happy with it. So the answer is 5. 9. 1/2 of 1/3 of 1/4 of 1/5 of a number is 2. What's the number? Again, exactly the same as question 5, whatever it was. Just try the numbers. I really think whoever wrote this question paper was trolling now, because based on my previous advice, you might want to start over here. But actually, the answer turns out to be A when you do some testing. So just start from A. 240 halved is 120. 1/3 of that is 40 divided by 3. 1/4 divided by 4 is 10. 1/5 divided by 5 is 2. So this one by trial and error works here. Again, some algebra would work there, but if you've got the answers, you can just test them all. And I'm convinced they put this one first on purpose, just in case you thought, oh, I'll try over here first and then go this way. But in any case, anyway, number 10. How many of these have a solution? X is 12. Well, 12 take away is 10. 2 is 10, so that's absolutely fine. That's good. 12 divided by 2 is 6, so that's not true. 10 minus 12 is -2, so that's not true. 2 times 12 is 24, take away 1 is 23, so that's not true either. Just one of them. I don't know how that was question 10, because it was far too easy. Anyway, this 3x3 grid, here it is, shows 9 1x1 squares, so each one of these is length 1, and uses 24 centimeters of wire. Okay, so it's just adding up all this, so 1, 2, 3, 4, 6, and so on to make 24. How much wire would be needed for a 20x20? Well, you just need to find a sensible way of counting here. So the way that I counted this was I said, okay, to make a 3x3 grid, you need 1, 2, 3, 4 rows of 3 centimeters across. And you need 4 columns of 3 centimeters down. So to make a 20x20, you still need one more row and one more column than what the grid is. So a 3x3 requires 4 rows and 4 columns. So a 20x20 requires 21 rows and 21 columns, but they're going to be 20 centimeters across and down, just like this is 3 across, because it's 3, that would be 20 across. So we just need to do, and of course to count this up, you just do 4 times 3 plus 4 times 3. To do this, you do 21 times 20 plus 21 times 20, and we get our answer of 840. Again, probably lots of other ways you could count that up, but that's just the way that I did it. There was a very similar question to this somewhere else that I saw. I think it was in the 2021 paper, Junior Maths Challenge, where they're asking you what fraction this whole shape is shaded. Now, probably the easiest way to do this is just to make the shape look all the same. Like, I don't like the fact that this is broken up into 4, and then these are big white triangles. Let's just break them up as well. And when you do that, you can just very easily see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 triangles, little triangles, and 3 of them are shaded, so that's just the answer. Very similar to a question in 21, I think, as well, in paper 2021, I mean. Okay, mean of 4 positive integers is 5. That means the total is 5 times 4 for 20. Because, of course, to find the mean, you add all the numbers up to find the total, then divide by the number that there are, 4, and you get the mean of 5. So do the opposite, multiply to find the total of the numbers. These are 4 integers, let's just put down some spaces here, and the median is 6. Now the median is in the middle of 2 numbers, so when it's in the middle you take the mean of the 2 other side. So actually, I don't really know what these numbers are, but I could just say they're 5 and 7, right? Because that would give me a median in the middle of 6, so that seems legit. These two answers add up to 12 currently, so I need another 8 somewhere. So let's just make this a 1 and this a 7. And then the mean of the largest and smallest is 1 plus 7 divided by 2, which is just 4. So the mean is 4. And you're probably thinking, okay, but you just made up a lot of stuff there, right? You just said that the mean is 6, so therefore this is 5 and 7. Why isn't it 6 and 6? Or 4 and 8? Well, it could have been. And it turns out when you do that, the answer will always just give you these two have a mean of 4, just like every time. And there's some maths you can do to prove that, but I'll leave that to you in your own time. This is a math challenge. We're just going to get the answers as quickly as possible and move on to the other questions. Question number 14. OLM is twice PON. So if PON was X, OLM would be 2 lots of x. It's twice as much. So that's this angle and this angle. Okay, so good. What can I start with? Well, if this is 124, then this on a straight line is 180 minus 124, which is 56. And now vertically opposite angles mean that this angle is x. And this angle here is just like this was 180 minus 124. This angle is 180 minus 2x. And now this triangle is a triangle, so it must add up to 180. So this plus this plus this is 180. And then we can just put this together, that's a minus x. Move the x over, move the 180 over, I guess, solve this however you want, but in any case you're going to get x is 56. Now that's not one of the answers, which is kind of them, because you just need to read again, they're asking for OLM, so they're actually asking for 2x, so you just double it and you say 2x is 112. Kind of them not to make 56 an answer, I thought. Question 15. 42 children play tennis or football or both. Now, as soon as I read this, I don't know whether it's because I've done a lot of Key Stage 4 maths in my life, but I just thought Venn diagram immediately with tennis and football. Okay, so for the same number play tennis, so in all of the tennis circle, the same number do this as play just football, which is just this crescent of the football circle. Now, if there are 42 children and the same number play tennis to just football, that means there must be 21 and 21. 21, now I've put it here because it's in the all of tennis. It's not this segment and it's not this crescent here. It's all of tennis, and 21 over here is just the crescent in here, which is why it's over on this side. Okay, twice as many play both tennis and football, so tennis and football isn't here, as just tennis. So of the 21 that are in this circle, twice as many are here as here. And without too much thought, it gets you 14 and 7. Essentially, that's a really fancy way of asking you to split 21 in the ratio 2 to 1. Add them up, get 3, divide it, but whatever. So 14 are here, 7 are there, because that's twice as many in here than in there. How many play football? Well, it's all of this circle, which is 14 plus 21 for 35. Probably lots of other ways to do it, but yeah, Venn diagrams are nice sometimes. You're given a sequence of digits this, and you can insert a decimal point at the beginning, at the end, or any of the other three. So here, 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 or there. Which of these can you not make? So let's just go through these. Let's put it right at the start first. This is now 625. It's going to do fractions here, not got a calculator. So it's 625 divided by 1, 2, 3, 4 zeros on your 10,000. So it's 65 over 10,000. Okay, well, let's divide both these things by 5, I guess. We get this. Again, they can still divide by 5 because they end in 5s and zeros, so divide it by 5 again. Divide that by 5 again. And then finally divide by 5 one more time and you get 1/16. So that's that one done, so that's fine. Next one, put the decimal point here instead. That's 65 over 1,000. Divide by 5. It's much easier now that you've done this one, because this is the same just with one less zero on the bottom, and you end up with this when you keep dividing by 5, which is one of the options. Put the decimal point here, same kind of thing, 65 over 100 this time. It's going to be the same as above except for one less zero on the bottom. Makes this eventually when you keep dividing by 5. Now that's this option here, so we've got all of these, so it's one of these two things. But like, I can kind of see, I'm going to do it one more time, but this isn't actually an option. But can you see how the fractions are getting bigger and bigger as you go along? So we can't get back down to here. Like the next one, 65, is actually just 25 squared anyway. But this is the one that we can't make because we kind of skipped it, right? This is a fraction less than 1, and we've kind of got done with all the fractions less than 1. So yeah, I can't do this. It's also, I think, here as a distraction because of this 625 setup. You think, oh, surely you can do that because it's 6 over 25, but no. Question 17. So all these squares have these lengths here. So the smallest is clearly 1, that's clearly this square. The next smallest is 4, that's clearly this square. 7 looks to be this square here, that looks to be the next smallest. 8, you don't have to do it by eye anymore, because if this square is 7, this square was 1, so this square is therefore necessarily 8. 9, for the same reason, is this one. 8 plus 1 makes this square 9. 10, same reason. You've got 9 across plus 1 there, so that's going to be 10 here. Then the next one's clearly 14, 15, 16, I think. Or sorry, 14, 15, 18. What's the area of the entire rectangle? Well, we just need to know the dimensions. So its height is 14 plus 10 plus 9, which is 33. And its width is 18 plus 14, which is 32. 33 times 32 takes a bit of work, but is 1056. Good. 17. Okay, how many two-digit primes have both their digits not prime? Well, just to give you an example here, 13 is prime, but 3 is prime as well, so this isn't one of the things that they're looking for. They want two-digit primes where both digits are not prime. Now, the only allowed digits, therefore, are 1, 4, 6, 8, and 9, because 2 and 3 are prime, so is 5, so is 7. So I'm only allowed to use numbers that use these digits, and they have to be 2 digits long. So actually, I was just super lazy here, and just wrote out every single number that can be made by this. I did it super systematically. I did 1, 1, 1, 4, 1, 6, 1, 8, 1, 9. Then I did 4, 1, 4, 4, 4, 6, 4, 8, 4, 9, and so on. Now, clearly, numbers that end in a 4, 6, or 8 are not prime. So we can just get rid of all those very quickly. If I was doing this for real, I wouldn't have even bothered writing those down, but may as well, because I'm just typing them anyway. 11 is prime, 19 is prime, 41 is prime, 49 is 7 times 7, so that doesn't work. 61 I think is prime, it's not in the timetables anywhere. I'm just going to say that it is. 69, these digits add up to 15. We saw earlier if digits add up to a multiple of 3, then it's a factor of, then it is a multiple of 3. 81 is 9 times 9. 89 and 91 feel prime, but I've done enough math challenges to know that 91 is it's 7 times 13. So that's not actually prime. And this can't be either, because again the digits add up to a multiple of 3. So we have 1, 2, 3, 4, 5 things that I'm pretty sure are prime. Good. Question number 19. So, okay, we've got this kind of grid that adds up to these numbers here, going across and down. Got to find out the values of j, k, and l. Well, there's a few ways to do this. I took the row and the column with the smallest number because I thought they would be easiest to work with. 2 j's and a k make 5, and 2 k's and a j make 7. Now, if you're fortunate enough to have done simultaneous equations, you can just do this properly, but I'm assuming that you haven't. So what I'm going to do is a bit of trial and error. I'm just going to say, well, what if j was 1? Sorry, what if j was 2? Therefore, k would have to be 1. 2 times 2 is 4, plus 1 is 5. Cool. Does that work here? Well, j is 2, plus 2 times 1 is 2. So that actually doesn't work. So this works here, but not there. Let's just try something else. J is 1, k is 3. 2 times 1 plus 3 is 5. 1 plus 2 times 3 is 6, which is plus 1 is 7, so that's good. So this is the solution. And now I can just look down here. J plus k plus l is 11, but I know j is 1 and k is 3. And I can get my answer as L is 7. Again, if you've done simultaneous equations, that question is much easier, but whatever. Okay, Edward makes a cube using 8 small cubes. Okay, if he used 8 small cubes, that means the dimension of the cube was 2 by 2 by 2. Literally, 2 times 2 is 4, times 2 is 8. But I'm saying this is a width times a length times a height, or length times width times height. This is the size of the cube that he's necessarily made. Samuel uses cubes of the same size to make a cuboid twice as long, 3 times wide, and 4 times as high. So his dimensions, twice as long means length 4, 3 times as wide means width 6, 4 times as high means height 8. And then we literally, again, this is the dimensions, so we just multiply these things together to find out how many squares there are. 4 times 6 is 24, 24 times 8 is 192. I know that because 25 times 8 is 200, and then you just take away 8. Now that's not an answer, again, question writers being kind to you, because if that was an answer I would 100% have circled it, but actually it's how many more cubes does Sam use than Edward? Edward used 8, he used 192, 192 minus 8 is 184. So they let you off with that one by not making 192 an option, I felt. Okay, 2 digits of both two numbers in the first calculation are swapped, and you make the same answer. So this is swapped and this is swapped, but you get the same answer miraculously. Which of these do the same thing? Again, you've got the answers, you just test them. So I worked out this times this is this, and I did that because timesing by 25 is actually kind of easy. You just times by 100 and then divide by 4. So this times by 100 is 3600, sorry, and then is 3600, and then divide by 4 is totally 900. So this should be 900, apologies. It doesn't actually matter for the purposes of this, but this should definitely be 900. I just wasn't concentrating very much. Anyway, when you swap the digits, you get this multiplication to do, And now remember, this is actually 900. But I'm not going to bother doing this, but I know if I did, the last digit would be a 2 times 3 for 6. Like imagine doing a column multiplication or whatever. The last digit is definitely a 6, because 2 times 3 is 6. The last digit of this, which should say 900, is 0. So this can't possibly be working, even though I haven't actually bothered to work out what this is, which is good, because apparently I don't know how to multiply anyway. Here, the last digit of this calculation is an 8, 4 times 2. When we swap the digits, the last digit, 3 times 4, is a 2. Because 3 times 4 is 12, you'd carry the 1. The last digit would be a 2. So this can't possibly be working, even though I haven't worked out what these are. Same thing here, just work out the last digit is a 4, because 4 times 6 is 24. Swap them over, last digit, 5 times 5 is 25, is a 5, so that can't work. These two last digit should be a 6, 2 times 8 is 16, carry the 1. Swap them over. 4 times 4 is also 16, carry the 1. So this could work, even though I haven't actually tested it. Here, when you swap the digit, when you multiply, you get ending in 6. Swap the digits, you get ending in 2, just like before. So that can't work. So the only one that has any chance of working is this one, even though I haven't bothered to work out what it is. Because it's the only one that could possibly work, it must therefore be the one that works. And I'll have my answer. So you get a square piece of paper, you fold it in half. So this is the way to fold it in half to make a rectangle, to make this rectangle, and then half again to form a rectangle that's not square. So she's not going to fold it this way because that would make a square. Going to fold it this way to make a very long rectangle. Perimeter of the second rectangle is 30. So the perimeter of this rectangle here is 30, because this is the first rectangle, this is the second. What's the area of the original square? So if we call this side length of the square x, that means this length is also x because it's a square, but this length is a half x. So this length is a half x, which means when you halve it again, you get a quarter x. But notice how this x hasn't changed. And so the perimeter of this shape is 30. We have x plus a quarter x plus a quarter x is 30. This is just 2.5x. And you could just do some trial and error here. 2.5 times 12 is 30, because you get to 24 times by 2, then add half of 12, which is 6, to make 30. Or you could say 2.5 is 5 halves. It's completely up to you. Times by 2 divided by 5, you get x is 12 either way. So this square has size 12 by 12. 12 times 12 is 144, and that will be my area of the original square. Only a few questions left, which is very good news for my voice. There's more than one integer greater than 1, which leaves a remainder of 1 when divided by each of the 4 smallest primes. So the 4 smallest primes are 2, 3, 5, 7. I'm looking for numbers which leave a remainder of 1 with all of these primes when you divide. Okay, so I don't know whether I just know things about maths that really helped me out when doing this question, but maybe if you're taking questions like question 23 seriously, you should also know some things about maths. But one thing about maths that's really cool is Euclid's proof that there are a different number of primes, and this is essentially what's going to happen here. And so I'm going to do a very similar thing to what he did, because this whole setup is exactly what he talked about. So do look up Euclid's proof of infinite primes if you can, because it's really interesting. But to make a number that's got remainder 1 for all of these primes, you just multiply the primes together. Now this number doesn't have remainder 1. This number is actually divisible by all of these primes, obviously, because you're multiplying these primes by something to make it. But if you just add 1, this number now has remainder 1 with all of these primes, because 210 is a multiple of them all, so adding 1, you just get remainder 1. Okay, so that's how you make one number that has remainder 1 divided by the 4 smallest primes. How do you make another? Well, you just times it by 2 again, right? Because the fact that there's 2 2's here doesn't make any difference. It's still going to have remainder 1 once you add that 1 on top with all of these 4 primes. And so these are the 2 smallest numbers that will do this. The difference between them, by the way, this is the next smallest because I times it by 2. If I had times it by 3, I would have made the next smallest after that. But I made the 2 smallest here, aside from 1 itself. The difference between them is 210, and so that would be my answer. Good. 2 questions to go. She's got 8 rows of 10 chairs, so let's just draw that out really quickly. 54 parents are sitting. Now there are 80 chairs, which is good to know. Every parent is either sitting on their own or next to just one person, so there's never a group of 3, because then the middle person would be sitting next to 2 people. So let's just try filling this out. So let's have this person sitting next to someone else. And then we can't have someone here because then this person will be sitting next to 2. So we have to leave someone here, put someone there. But then we can put someone there, because then these two can sit together, but we have to leave one, and so on. And we can also put someone here. Now, the reason I'm trying to put as many people as possible here is because it's saying what's the largest number of adjacent empty squares. So if I fill up from the front as much as I possibly can without breaking these rules here, then I'll have as many spaces as possible at the back. So I'm just going to do that setup quite a few times. And now if I do that 7 times, there are 7 people on each row. 7 times 7 is 49. So I only have 5 more parents left to sit. So I'll do the same thing. There's 2 of them. There's another 2, so only 1 more parent left to sit. I could put them there, leaving 3 chairs empty next to each other, or I could put them all the way over here, leaving 4 chairs empty next to each other. And so the most possible number is those 4 chairs next to each other there. Quite a weird and interesting question. Question 25, this is just straight up hard. This is just I think, quite a difficult question. You've got to do quite a lot of staring to get it, I think. Vertically opposite angle says this angle is 2y and this one is 2x. That's the first thing I can say. Now this angle here it's on a straight line, so it's 180 minus 2y minus x. Like imagine this was 50 and this was 30, this angle would be 180 minus 50 minus 30, for whatever that is. So it's 180 minus those two. This angle here is the same thing, 180 minus these two, which is slightly different. The letters are kind of swapped around, see? Okay, well, how is this helpful? Well, looking at this triangle, like somehow I have to use this 33 degrees thing, because it's the only actual number I have. So this looking at this triangle, 180 equals this angle plus this angle plus this angle. So that's what I've written there. 180 is this angle plus this one plus 33. Let's sort this all out. Now I know there's x's and y's here. Divide by 3 here and we get x plus y is 71, which isn't amazingly helpful. But I think I only knew what I was doing here because I've seen questions that do a similar thing before, and because I was just trying stuff. But now, if we look at this whole triangle over here, so this triangle here instead, maybe we just say 2y plus 2x plus this angle here. I don't know why I've called it jk. Oh yeah, jkl. This angle here, jk to l. This angle. This plus that must be 180. And now, okay, sure, I don't know what x and y are, but I know x plus y is 71 from the first triangle I looked at. So therefore 2x plus 2y is 142, doubling them up. And I can just replace this 2x plus 2y with that figure there. And of course then I can get my answer of 38. A really tough question, I thought. If you haven't seen something like that before using this kind of trick, it would have been very difficult to get. I don't imagine that many higher GCSE kids would have got that either. But I mean, it's question 25, so maybe it's fair that they put something that's pretty difficult in the end there. Really well done for preparing yourself nicely for UK Maths Challenge, and thank you for watching.